Good morning, students. In this video we are going to see about a sequential circuit, and we are just starting about a sequential circuit, and we have seen a combination logic circuit and about the design of combination logic circuit, and we know what is combination logic circuit. Combination logic circuit, the output depends on the present input. This is the combination logic circuit. The output depends on the present input. That is said to be the combination logic circuit. Whereas sequential logic circuit, in sequential logic circuit, the output of the circuit not only depends on the input but also depends on the output, previous output. This is said to be the previous output, or in other words, output depends on input plus your previous output. Okay, your previous output. This is said to be your sequential circuit. Okay, this is said to be your sequential circuit. So I am saying previous input and previous output. I am saying previous output. So this output you will get it through a memory. You will get it through a memory. This memory is nothing but your flip-flop. This is a single bit data storage unit. Single bit data storage unit. It may be a single bit data storage unit, and that flip-flop is a single bit data storage unit which can store binary 0 or binary 1. Binary 0 or binary 1. So if I am telling this as an 8-bit memory, you will be having 8 flip-flops. You will be having 8 flip-flops. As of now, you just remember you have a flip-flop in the memory. You have a flip-flop in the memory. That flip-flop will work along with the clock signal. This is the clock signal. Okay. So input to the flip-flop will be the output, present output, and the clock signal. And this is said to be sequential circuit. This is said to be sequential circuit. I repeat, sequential circuit will have an output with the current input and the previous output. Whereas to get the previous output, you will be getting the previous output from the memory. Memory, you will be having a combination of flip-flop. Let us assume here we have only one flip-flop. This flip-flop will have an input as the current output of the combination logic circuit along with the clock signal. Okay, along with the clock signal. So this is said to be sequential circuit. Sequential circuit will have a clock also. Okay, keep in mind, we will have a clock also. You have a clock signal. So let us differentiate between your combination logic circuit and the sequential logic circuit. So combination logic circuit, the output is determined by the present values of input only, that we know, right? And whereas your combination logic circuit does not have a memory. Okay, does not have a memory. That is what it was drawn in the previous slide. Here, combination logic circuit doesn't have a memory. And it does not have a feedback path. Only if you have memory, you need a feedback path. Here, there is no feedback path. And its operation can be described by the truth table. Okay, you have a truth table. Whenever you want to do an operation, what is the first step you will go ahead? You will try to draw the truth table, and then you will go ahead with a K-map or any sort of logical minimization, and then you will implement the circuit. I hope you remember that. The same thing I am repeating here. Its operation can be described by the truth table, and it does not have a clock signal. Okay, its action does not depend on the clock transition. Does not have a clock signal. See, it doesn't have a clock signal. Here, whereas the sequential circuit, it has a clock signal. The operation is related to the clock signal. Meaning, whenever you have a clock signal or whenever you have a transition in the clock signal, you have an output. Whenever you have a transition in the clock signal, you have an output. Meaning, all the operation of the sequential circuit will be synchronized with respect to clock. We can tell like that. Okay, and then the circuit is very simple than that of sequential circuit. Combination logic circuit is very simple because you don't have a feedback path, right? So, and it can be built by using the basic logic gates. An example, you have read about your adder, subtractor, multiplexer, demultiplexer, decoder, and the comparator. Okay. So come back to the sequential circuit. So the output is determined by the present values of input as well as the previous output or the past values of the output. It has a memory and a feedback path from output to input. That is what given in the circuit diagram. It has a memory and it has a feedback path. And this operation can be described by the truth table and the timing diagram. Here also you have a truth table, but here you will also focus on the timing diagram, because all the operation of the sequential circuit is synchronized with respect to the clock, right? So you will be explaining the operation of the sequential circuit with respect to the clock pulse. So with respect to the timing diagram, you will explain the sequential circuit, or you will design the sequential circuit. So it may or may not have the clock signal. See, you have two types of sequential circuit. One is said to be synchronous sequential circuit and another one is said to be asynchronous sequential circuit. Synchronous sequential circuit, in the sense, all the elements inside the synchronous sequential circuit or in the sequential circuit will be synchronized with respect to the common clock, whereas asynchronous sequential circuit, all the elements of the sequential circuit, okay, does not have a common clock, Sometimes you may have a clock or you may not have a clock also, okay, but mostly the synchronous sequential circuit or sequential circuit will have a clock. And this circuit is more complex because you have a feedback path, right? And with the help of memory and the clock signal, so this circuit is complex. And it can be built by using logic circuit and the combination logic circuit. Examples are flip-flops, counter and shift register. Okay. So let us go ahead with the content of today's class. So today we are going to cover the flip-flops. Okay. We are going to cover the flip-flops. Later we will go ahead with the register and how to design a sequential circuit, maybe synchronous or asynchronous. And later we will go ahead with the counter. Okay, later we will go ahead with the counter. The first, today we are going to cover the content of flip-flop. So flip-flop, as I said, is a 1-bit memory storage unit. It is a single bit memory storage unit. It can store either 0 or 1, binary 0 or binary 1. It can store either binary 0 or binary 1. There are 4 types of flip-flops. Which is nothing but SR flip-flop, and I am writing it flip-flop as FF, SR flip-flop, D flip-flop, JK flip-flop and T flip-flop. Okay, SR flip-flop, D flip-flop, JK flip-flop and T flip-flop. SR is said to be set reset flip-flop. Okay, set reset flip-flop. D is said to be delay flip-flop. JK is simply JK flip-flop. T is otherwise said to be toggle flip-flop. Okay, it is otherwise said to be toggle flip-flop. Let us go ahead with the SR flip-flop first. Okay. So the SR flip-flop, the circuit diagram of SR flip-flop is this. So in the circuit diagram, we are going to for all the flip-flops, or all the flip-flops here, whichever we are going to discuss, will be realized by using NAND gates, universal gate, NAND gate. And you know what is NAND gate and how your NAND gate will be. So NAND gate, we know that we know what is the NAND gate. NAND gate, you have when any one of the input is 0, your output will be 1. That is your NAND gate truth table. So truth table, if I have A, B for the NAND gate, let me have C for the as the output. So A, B, C. So 0, 0, 0, 1, 1, 0, 1, 1. When any one of the input is 0, the output will be 1. Okay. So except for 1, 1 combination, for all the inputs, for all the combination of inputs, the NAND gate will be having a 1. Okay. So here all the flip-flops that we are considering here, we will be designing by using the NAND gate, and I will be implementing all the flip-flops using NAND gates. The same type of flip-flops can be read by using the universal NOR gate too. Okay, right. So SR flip-flop, as I said, you have two inputs, set and reset. Okay, set and reset, you have two inputs. Okay. So now let me draw the circuit diagram of the SR flip-flop. This is said to be synchronous. These flip-flops are said to be synchronous. This will come under synchronous sequential circuit. Okay, synchronous sequential circuit. So what is synchronous sequential circuit? As I already discussed, all the elements of the sequential circuit will be given a common clock, will have a common clock. Or what can I say is, all the elements of the sequential circuit will be synchronized to the same clock. Okay. So like our operation, the day-to-day activity of a human being is synchronized with respect to the clock. Similarly, the sequential circuit operation will be synchronized with respect to the clock. Okay. So D flip-flop, as I said, we are going to draw it with NAND gates. We are going to implement with respect to NAND gate. So I will be having 4 NAND gates. Let me name the NAND gates as 1, 2, 3 and 4. Okay. So this SR flip-flop will be having, all the flip-flops will be having two stages. This is the first stage and this is the second stage. So here you have two inputs. So in the first stage, namely the gates 1 and 2, one among the two inputs of gates 1 and 2 will be connected to the clock, will be connected to the common clock. And the next input, one is your set input and another one is your reset input. Okay, you have two inputs. Whereas here, as I said already, sequential circuit depends on the present input as well as the previous output. So take this previous output and give it as the input. Okay. And similarly take this and give it here in the second stage. Okay. So this second stage is otherwise said to be latch. So the difference between your flip-flop and the latch is, the latch does not have a clock. Okay, the latch won't be having a clock. This we will read it in asynchronous sequential circuit. As of now, this is also a single bit memory storage unit, but it won't have a clock. Okay. So this output, I will be naming it as the third, from the third gate. This is said to be Q and this is said to be Q bar. Okay, this is said to be Q bar. Is it okay? So when we are deriving the truth table of the SR flip-flop, we not only consider the SR input, we will also consider the previous output, namely Q. Here I am telling it as Q. Okay, because previous output will act as the input, So Q, so we will also consider Q as the one of the input. Okay. So I am telling it as we are having a clock. I repeat, we are having a clock here. So here this clock, let me have a positive clock. Okay. Positive clock in the sense, this particular gate will respond, or this particular flip-flop will respond only when we have a high clock pulse. Okay, only when we have. So clock pulse is nothing but we have a repeated sequence, periodic, it is a periodic waveform or a repeated sequence of periodic waveform. This is your clock. This is your clock. Evenly you have on and off. Okay. So let it be the first clock pulse, second clock pulse, on and off, and this is the third clock pulse. Here this clock can also be, I can say we have two types of clock for sequential circuit. One is said to be your level triggered clock, and another one is said to be edge triggered clock. Okay. Again, each of the two cases, namely level triggered and edge triggered, will be classified as positive level triggered and negative level triggered, whereas edge triggered, positive edge triggered and negative edge triggered. Okay, negative edge triggered. I'll tell you what is that. Okay, so positive level triggered. So I'm having a clock here. So I'm talking about level triggered now. So let me write it as this as 0. Okay, 1, 2, 3, 4, 5, 6. All are in seconds. Okay. Level triggered means whenever, and this is nothing but, let me take this clock pulse as this logic 0 is at 0 volt and logic 1 is at 5 volt. Okay, logic 0 is at 0 volt and logic 1 is at 5 volt. Okay, so logic 0 is equal to 0 volts means here this one. Okay, so whenever there is a change in state from 0 to 1, okay, 0 to 1, from 0 it is going to 1, from 0 volt it is going to 5 volt. This is said to be positive. This is said to be whenever it is going from 0 to 5 volt or 0 to 1, this is said to be positive edge triggered. Meaning whenever you have a transition, whenever you are designing a flip-flop in the positive edge triggered, I'm sorry, I'm talking about the edge triggered, it's not level. Whenever I'm talking about positive edge triggered means whenever I have a change in transition from 0 to 1, there will be change in the corresponding output. There will be change in the corresponding output. Meaning whenever there is a change from 0 to 1, at that time whatever is the input of your SR flip-flop, okay, that will be taken into consideration and your flip-flop will respond only during that period. Okay, only during that period. Meaning positive edge triggered means whenever you have a change from 0 to 1, from 0 to 1, okay, high. So during this period you have a transition in the output. You have a transition. Whenever you have a clock transition, positive clock transition, you have a change in the output. And similarly, whenever you have a change in the side, meaning the right side, from high to low, 5 to 0 volt. When you have a change from 5 to 0 volt, this is said to be negative edge triggered because it's the falling edge of the clock signal, right? This is said to be negative edge triggered. So we can also design the flip-flop such that your flip-flop will respond whenever you have a change from 5 to 0. Okay, this is said to be negative edge triggered. And what is said to be level triggered? Level triggered, and again let me draw the clock signal. So I have a 0, I have a 5 volt, 0, 5 volt, 0, 5 volt, and I have 0, 1, 2, 3, 4, 5, 6, all are in seconds. So now I am talking about level triggered. I have two levels. One is logic 0 level and another one is logic 1 level, which is nothing but 5 volt. I have 0 volt here. So when I am telling positive level triggered, meaning your flip-flop will respond only during this period. Whatever may be the input change during this period, you have a corresponding output. You have a corresponding output in this period in the flip-flop. This is said to be positive level triggered because your output will be changed with respect to the input okay, there will be a response due to the change in the input due to this only during this positive state, 5 volt state, whereas negative level triggered is nothing but output of the flip flop will depend or the output of the flip flop will change with respect to the input only during this period, negative level triggered period. Two levels you have, 5 volt level and 0 volt level. Is it okay? And the main drawback in level triggered is if your length of the pulse or the period of the pulse is larger, maybe your on period and off period is larger, your output, see during this period whatever, this is, consider this as a black box, let me consider a long on pulse. So during this, if I am changing the input rapidly, your output will also change rapidly. Your output will also change rapidly. So you won't get a constant output. Okay, you don't get a constant output. So mostly it will be good if you go ahead with your edge triggered design. Okay, but here I am considering, for understanding, I am considering all level triggered, and that too positive level triggered, meaning whenever your clock is 1 or high, your system will respond. System in the sense your flip flop will respond. So I am considering a positive flip flop, and that too level triggered, positive level triggered clock pulse. I am considering this here. Throughout the discussion I am going to consider this only. Right. So I have discussed about this clock. Let me come ahead with your flip flop again. So we have a clock, we have an input, and you have the one more input, which is nothing but the previous output of the flip flop. Previous output will be connected to the input. This is also one more input. So we have, let me classify here as, so I am telling previous input. So previous output will be, previous output or past output will be connected to as the input. Am I right? Will be connected as the input. Let this be Q, SR input, SR input of the flip flop, and another one is Q, because this is also going to act as the input. Am I right? This is otherwise said to be, previous or the past input state is said to be Q, otherwise this is your present state. I will tell you what is this present state. 3 combinations of input, you will be having an output. This will be termed as Q plus and Q bar plus, where Q plus and Q bar plus is said to be your output, and that too the next state. So the output during this clock cycle, namely the first clock cycle, let me take this as a second clock cycle. The output during the first clock cycle, let me term it as Q, that is going to be the input of the flip flop. Okay, so the output in the next clock cycle, let it be Q plus. Okay, so this is the next state output, this is the present state output, which is going to be the input of the flip flop, which is going to be the input of the flip flop. So let us consider the states. We will distinguish here this as a state. So there will be a state, or there is a state for each and every flip flop. Okay, there is a state for each and every flip flop, namely the present state and the next state. Present state is determined as Q, or set to be Q, and the next state is set to be Q plus. That will happen during the next clock transition or the next clock pulse. Okay, so now, so as I said earlier, you have 2 inputs, sorry, 3 inputs. One is your S, R, and your Q, and another one is Q plus and Q bar plus. So again let me draw the circuit diagram. This is Q, this is Q bar, and we are tying this to the clock. This is R, S, and this is R. Okay, so 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 1 1 1. Okay, so this is nothing but Q, which is nothing but your present state, S R, Q plus, this is said to be your next state, Q bar plus. Okay, so this is the first input combination, second, third, fourth, 5, 6, 7 and 8, and R is 0 now. S and R is 0 now. S is 0, R is 0, right? S is 0 and R is 0. And we know this is your clock and this is positive level triggered clock. Consider this is always 1. So whenever we have the NAND gate, whenever one of the input is 0, output is 1. So here also 0 1, output is 1. Okay, so here one of the input is 1 and another input of this gate is also 1. So this gate let us name it as 1 2 3 and 4. Okay, one of the input of third gate is 1 and the second input is 1. So we cannot determine this Q unless and until if you know the second input, because what is the truth table of the NAND gate? If any one of the input is 0, you will have your output to be 1, but for both 1 combinations you will be having your output is 0. So we don't know what is this input, and similarly what is this input. Now you need to consider this present state input. Okay, so now this output, okay, the next state output depends on the previous output. What is your previous output? Previous output, here we have considered it as 0. Okay, here we have considered it as 0. So this Q is 0 now. So this is 0. Now this is 0. So one of the input is 0. The output will be 1. Output will be 1. So this 1 will go here. So 1 and 1, your output is 0. Okay. So now what is your Q plus? Q plus is 0. And what is your Q bar plus? That is 1. And keep in mind, this Q and Q bar will be complement with respect to each other. Okay, will be complement with respect to each other. Right. So let me go ahead with this 0 0 combination also. With this 0 0 combination also. Okay. So again 0 0 1. Okay. 1 will be having 1 clock pulse here. Again you will be having 1 and 1 at the output. As I already said, since I am having 1 and 1 at the first stage of your NAND gate, the output of the flip-flop will depend on the previous input. What is our previous input? The previous input here it is 1. The previous input here it is 1. So the previous input is 1. Okay, the previous input is 1. So the previous input is 1. So 1 and 1, your output is 0. And this 0 goes here. 0 and 1, this will be 1. Right? 1 and 1, your output is 0. 0 and 1, your output will be 1. So for 1 0 0 combination, your output is 1 and 0. Your output is 1 and 0. Right? 1 and 0. So this is your first row, second row, third row, fourth row, fifth row, sixth row, seventh and the 8th. Okay. Right. So now let me go ahead here again. Let me go ahead with the next input combination. The next input combination is 0 and 1. The next input combination is 0 and 1. So when your input is 0 and 1, okay, so we know that when any one of the input is 0, your output is 1. And here the second gate, both are 1, your output is 0. And here see, the input to the fourth gate is 0, so I can say this is 1. And if this is 1, this is also 1, and 1 1, your output is 0. Right? So look here, for this combination of input, namely 0 and 1, your output does not depend on the previous state. Your output 0 and 1 does not depend on the previous state. We haven't carried out your q here to derive our output q plus and your q bar plus as like your input combination 0 and 0. So your output is completely independent of the present state. It is completely independent of the present state. So what is this combination of output we have? 0 and 1. So 0 and 1. Okay. So again, let me go ahead with this combination also. So as I said, for 0 1 combination, output is completely independent of the present state. So completely independent of the present state means you will be getting the same output. We can even derive again. Okay. So again your input combination is 0 1 0 1. I will be getting 1 over here. I will be getting 0 over here. I will be getting 1 over here because 0 is the input. This one will be carried forward. 1 1 1 is 0. So this will be 0 1 and again 0 and 1. Okay. So let me go ahead with the third combination again. So this is 1 0. If your input is 1 0, what will be there at the output? Okay. So when you have 1 0, so this will be 1. So 1 and 1, this will be 0. And when one of the input is 0, this will be 1. So again, one of the input of the third NAND is 0. So this will be 1. This is carried here, 1 and 1. This output is 0. Okay. So when here also for this state, okay, for this 0 1 0 state, or when your input is 1 0, okay, when your input is 1 0, your output again, or the next state output, I can say, it does not depend on the previous output. Okay, or it does not depend upon the present state. I can even say like that. So let me write it here. So for 1 0, I will be getting 1 0 only. Again for 1 0, I will be getting 1 0. You can work out. Let me come ahead with 1 and 1. Okay, with 1 and 1, what will be your output? So if both inputs are 1 and 1, so we know the clock is high. If 1 and 1 is the input, your output is 0 and 0. If this is 0, one of the input of third and fourth is 0, both are 1. So you have a contradictory output here. See, both are 1. But what I said, Q and Q bar are complement with respect to each other. Okay. But I am getting 1 and 1 here. This I am getting it as 1 and 1. So I am getting it as 1 and 1. Okay. So when my input is 1 and 1, your output is also 1 and 1. The same case here also. This state is said to be indeterminate state. This state is said to be indeterminate state, and this should not, we should not have this combination. We should not have this input combination at all, because one should be the complement of with respect to the other. Like that only you should get your output. Okay. So hence this state is said to be indeterminate state. And it's not a reliable state, and mostly we won't be use this combination at all in SR flip-flop. Okay, we won't be using this state in the SR flip-flop. So whenever we are using this SR flip-flop, ensure that this 1 and 1 combination should never occur, because this is said to be in not reliable state, otherwise an indeterminate state combination. Okay, indeterminate state combination. Here this state is said to be indeterminate state. Indeterminate state, this should not happen at all. Ensure that this should not happen. Okay, this state is said to be indeterminate. So now let me see each and every row and tell this either it is set state or reset state, like that. Okay. So this is set and this is set input, this is reset input. In general we know set means logic 1, reset means logic 0. In general we know that set means logic 1 and reset means logic 0. Now for the input combination 0 and 0, for the input combination 0 and 0, the next state is same as the present state. The next state is same as the present state. Look here, for the input combination 0 and 0, the next state is same as the present state. Same as the present state. Hence, this state is said to be, these two states, okay, are said to be no change states. These two states are said to be no change state because the next state is same as the present state, okay. And the next one, let me go ahead with a combination of 0 and 1, 0 and 1, 0 and 1, okay. Look ahead with this combination. I have 0 here and I have 0 here, and similarly 0 and 1, I have 0 here, I have 0 here, I have 0 here, 0 here, I have 1 here, 0 here. See, whatever may be the present state, either 0 or 1, my next state is 0 only. My next state is 0 only. Hence, this is said to be, what is said to be? If it is 0 means it is said to be reset state. Okay, this is said to be reset state. Okay, let me write this. This is reset state. This is reset state. Okay, let me go ahead with the next combination 1 0. So when you have 1 0 combination here, when I have 1 0 combination, again look ahead with your next input, present state and the next state output. So I have 0 here, I have 1 here, I have 1 here, I have 1 here. So whatever may be the present state combination, see I have 0 and 1 here, but what is my next state? 1 and 1, it is in the set mode, it is in the set mode. Hence I can say this is in that state, this is in set state. This state is said to be set state. And I won't consider the indeterminate state because we will see to that this combination will never occur. Okay, so we have altogether 2 no change state, 2 reset state and 2 set state. Okay, this is your truth table. This is your truth table. This is said to be the truth table. So while reading about the flip-flop, while discussing about the flip-flop, we should also consider one more table, namely this excitation table. This will be helpful while designing your circuit, sequential circuit. Okay. With the knowledge of your output, with the knowledge of the present state and the next state, we can determine what is the input. We can determine what is the input. With the knowledge of the present state and the next state, we can determine what is the input. The present state is said to be Q and the next state is said to be Q plus, and what is the input here? S and R. 4 possible in combination, it's not combination, 4 possible input I should not say, it is 0 0, 0 1, 1 0 and 1 1. Okay, so now let me go ahead with the previous table. Okay, so whenever my Q and Q plus is 0, what about my S and R? S takes the value of 0 and R takes 0 and 1. Don't case state. I don't know whether it is 0 or 1. So here how will I fill this? S takes the value of 0, R takes the value of X. Okay. Next let me go ahead with the 0 and 1 combination. This is 0 and 1. I won't be considering this indeterminate state. Okay. So this is 0 and 1. For that combination, this is 1 and 0. Okay, for that combination, this is 1 0. And then what is the next one? 1 0 combination. 1 0 combination. This is 1 0 combination. Only we have only one 1 0 combination. This 1 0 combination, S takes the value of 0 and R takes the value of 1. So S takes the value of 0 and R takes the value of 1. And what is the next one? 1 1 combination. 1 1 combination. So for both 1 1 combination, R take the value of 0 but S takes 0 and 1. So I will write it as X 0. Okay, X 0. This is about the excitation table of your SR flip flop. Okay. What is the disadvantage of SR flip flop? We should ensure that we should not have an indeterminate state. Avoid the indeterminate state of your SR flip flop. We have to ensure that the complement of S input should occur at the R input. Only then you can avoid your SR flip flop. So to go ahead with this, we will derive a new flip flop called D flip flop.
Okay, to avoid the indeterminate state of your SR flip flop, we have to ensure that the complement of S input should occur at the R input. Only then you can avoid your SR flip flop. So to go ahead with this, we will derive a new flip flop called D flip flop in the next slide.